Okay, good afternoon. So I'm Aki Roberge from NASA's Goddard Space Flight Center. And so you've heard a lot about Habitable Worlds Observatory over the week, heard it mentioned a lot. And I've been asked to tell you some more about it. So what it is, where it came from, and what's actually going on right now. And you've also heard a lot about the ELTs this week, and so I'm not going to repeat that stuff. I'm just going to take a little bit of time to talk about the complementarity between Habitable Worlds Observatory and the ELTs in terms of the science. Okay, let's get going. So what is it? So it is NASA's next flagship mission concept that was recommended by the Astro 2020 Decadal Survey. It is a large aperture, UV optical near-infrared space observatory that basically a super Hubble. And like Hubble, it would be capable of performing a wide range of transformative astrophysics. But unlike Hubble, it would be the first telescope actually designed to search for signs of life on planets outside the solar system. And this quote from the Astro 2020 Decadal Survey report, I mean, first of all, I find it incredibly inspiring. But at the same point, I also find inspiring that they've embedded in here something really important. If planets like Earth are rare, our own world becomes even more precious. So embedded in here is part of the science goal, is that we want this observatory to be powerful and robust enough that we can find out if planets like Earth are common or rare. And that implies something about the sample size of targets that you need to be able to study. Okay, so this science goal didn't come out of nowhere. Obviously, humans have been thinking about it for centuries, maybe millennia. And looking a little more recently, there have been many reports over the last decade plus now, that had a general consensus about the search for life in the universe. First of all, that it would be a momentous achievement. But second of all, that there are two paths that we can pursue towards that goal. And path one, space-based direct spectroscopy for sun-like stars. Path two, ground-based direct spectroscopy for planets around low-mass stars. So I'm going to take just a few minutes to really, at a high level, summarize the logic that went into that consensus. Okay, so first of all, for sun-like stars and potentially habitable planets, so that means terrestrial planets that have would have a high mean molecular weight atmospheres. They're small planets with small atmospheres. Sun-like stars with the star is large, so that the signals of those atmospheres in transit spectroscopy are extremely small. That means we need a different technique. So the thought is that transit spectroscopy won't do it. We'll have to go to direct spectroscopy. Okay. But Earth-like planet around a sun-like star, as you've already heard, the contrast, the planet-to-star flux ratio is extreme, 10 to the minus 10. The required ultra-high contrast appears to be too challenging from the ground for these potentially habitable planets around sun-like stars, even using the ELTs, future extreme adaptive optics, and other advanced techniques. So the thought there, that all those reports came to the consensus, was that we need space-based direct spectroscopy to reach those extreme contrast goals. But on the other hand, we turn over to the low-mass stars. We still have a small planet and a small atmosphere, but now the star is smaller too. So, you know, instead of having vanishingly small signals in transit spectroscopy, we only have small signals in transit spectroscopy. However, transit spectroscopy is inherently sensitive to the planet's upper atmosphere. And there are some really important molecules that are relevant for habitability that are concentrated, that we believe will be concentrated in the lower atmosphere. For example, water vapor, which in Earth's atmosphere is really concentrated in the troposphere, so the lowest part of Earth's atmosphere. So again, we come back to, hey, we think we need direct spectroscopy for potentially habitable planets around low-mass stars in order to probe the lower atmosphere and maybe reach all the way to the surface. But again, the contrast requirements are more favorable. With the lower mass star, The smaller habitable zones, that means the planet is brighter. So the planet to star flux ratio has gotten more favorable. So, okay, we can try ground-based spectroscopy for this one. And so this is the basic logic behind all of those reports coming to these sort of like the two paths for, to approach habitable planets. Okay, so I'm going to move to Habitable Worlds Observatory science. So like Hubble, it will be able to do a vast range of astrophysics, all the topics that were studied with Hubble and more. I obviously don't have time to go into it all, so I'm just going to hit a few highlights here. Okay, so first of all, let's look back at the decadal for a second. This is sort of our foundational document for Habitable Worlds Observatory. There were 3 science themes. The first science theme was worlds and suns in context, pathways to habitable planets, with a focus area in pathways to habitable planets. Theme 2, new messengers and new physics, and cosmic ecosystems, unveiling drivers of galaxy growth. And the decadal survey said, Habitable Worlds Observatory is in fact, despite the name of the observatory, it is our mandate is to serve both of these themes. Okay, so another Earth. So this is what we are going for. High contrast image of a planetary system that looks like the solar system and actually has a pale blue dot in it right there. So let's take a minute to think about what the implications are. So the Earth in V-band is about 30th magnitude, and that is a key driver of the observatory's sensitivity. But we're not here to just take pretty pictures of pale blue dots. To understand habitability, to search for life, we need spectroscopy. And we want direct spectroscopy, we want the light directly reflected from the planet with as little leaked starlight mixed in as possible. Again, let's take a look at a few key numbers. There's the planet to star flux ratio, 10 to the minus 10 over there. And that is a key driver of the telescope stability, because as you heard this week, the worse your wavefront error is coming into your chronograph, the worse your chronograph performs. And we really need an excellent wavefront hitting a high performance chronograph here. Okay, some other key factors. We spend a lot of time thinking about not just the modern Earth, but the Earth through time, because the Earth has only actually looked like the modern Earth with this very high oxygen concentration in it for about 13% of Earth's inhabited history. But still, we understand the modern Earth really well, so it's still a good touchstone. And there's a key biosignature right there is molecular oxygen. And that is an inherently pretty narrow molecular absorption feature. And so that is a key driver of the spectral resolution that we need for Habitable Worlds Observatory for the direct spectroscopy. Okay, then we turn to the Proterozoic Earth, so, which was almost half of Earth's inhabited history. At this time, the oxygen levels in the atmosphere were much lower. And if you look closely, the molecular oxygen feature is almost undetectable. It's really small. Let me see, how does this thingy work? Whoa, okay, there. However, ozone, on the other hand, in modern Earth, this ozone absorption band right here is really, it's actually too strong. We should be glad about that. That's actually protecting us from getting, cooked. But it's too strong for good abundance measurement. In the Proterozoic, however, when the oxygen levels are lower, ozone becomes a really good biosignature. It's sensitive, but not too strong. And so the desire to be able to observe that molecule is a key driver of the chronograph's short wavelength cutoff. And then we turn to the Archean Earth, at which time there was no oxygen and no free oxygen in the atmosphere. Instead, there was a great deal of methane being produced by bacteria, so that is a biosignature there. But right there's another really important molecule right there, CO2, which is an important greenhouse gas dictating the sort of the climate of the planet, on top of which in some contexts it's actually, in some contexts paired with other molecules, it's also a biosignature. And so that is a key driver of the chronograph's long wavelength cutoff. So that's kind of how, like, sort of a flavor of how the science plays into your instrument, your observation requirements and your instrument requirements. Okay, but HabWorlds won't only do habitable exoplanets. For example, during a habitable planet survey, you also detect hundreds of other different kinds of planets, just because most planets are in multi-planet systems. And so for those planets, would be able to do high quality direct and transit spectroscopy, because pretty much as a rule, except for Mars, they're all brighter than the Earth, except for Mars. Okay, but again, I just want to emphasize, Habitable Worlds Observatory is not only for exoplanets. Key drivers in galaxy growth and evolution require the far UV capabilities of this observatory. And so this is just showing you what's happening. I wonder if, I don't dare try to play it again. It shows you if you're only looking in the optical and looking at the stars and the dust, you're really missing a lot of what's happening with the evolution of this galaxy. So the red gas is emitting in X-rays, and all the green gas there is emitting in the far UV. So this is really important driver for us. Also, to understand the building blocks of galaxies, and also to put constraints on the properties of dark matter, we want to be able to study low-mass galaxies at moderate redshift here. And so here, these very low-mass dwarf galaxies are sensitive probes, cosmological probes, and also probes of the characteristics of dark matter. So to Hubble, that's, it's basically just a little smudge. But to HabWorlds, that's key, being able to get that kind of resolution, so you can you can actually start to look at the individual clusters in this dwarf galaxy, look at their motions, and start to understand what the dark matter halos might look like here. Okay, and solar system. So Hubble was amazing for solar systems, so is JWST, and with Habitable Worlds Observatory, it will also be amazing. Depending on the exact size of Habitable Worlds Observatory, we could in fact get sort of near flyby quality imaging out to about the orbit of Jupiter, out to the Jovian system. And this is one of I really like Ceres, actually. It's my favorite dwarf planet. So, because look at that. Okay, that's not the right thing, sorry. Okay, there. This spot right here is an eruption of salty water, salty liquid water that has recently come out from the interior of this dwarf planet. So I think it's another place it's a place where there's potential for habitable conditions that doesn't get talked about as much, because everybody just talks about Europa and Enceladus. Okay, so now I'm going to talk a bit about HabWorlds, its past and present, so where it came from. Okay, so speaking of the long development timescales, and I could actually, this history of HabWorlds actually could start earlier, but I just went back, to the last decadal, Astro 2010. And so at that time, sort of an astrophysics-focused observatory was sort of proposed for technology development. It was called ATLAST. And nothing happened. But then at about 2013, some stuff started happening. At Goddard, we did an internal study, concept study for ATLAST, but instead tried to make it more exoplanet focused, like get more optimized for exoplanets. And at about the same time, there were 2 exoplanet probe concept studies led by JPL, exoplanet probe Starshade and exoplanet probe Chronograph. Some of us in this room were involved in those. And then after that, headquarters started up 4 concept studies for 4 flagships to basically prepare for submission to the Astro 2020 decadal. So the 2 that matter here right now are LUVOIR, and I was the study scientist for that one, and HabEx, and Bertrand was the study scientist for that one. And all of those went into the Astro 2020 decadal, and then we spent some time, waiting for deliberations. And those two concepts directly fed into Habitable Worlds Observatory. And so, these are the few of the key recommendations or expectations for Hab Worlds coming out of Astro 2020. They said an off-axis telescope with a 6-meter twiddle, 6-meter inner diameter. And we'll talk, I'll come back again, what does this inner diameter thing mean in a moment. Enter phase A this decade, so in other words, they mean before the next decadal. And they expected that it could launch in the first half of the 2040s. Okay, so just quick recap on LUVOIR and HabEx. I'm not going to spend much time on this, but for LUVOIR, we studied two architectures. A wavelength range from the far ultraviolet into the near infrared. 4 instruments, which I'll talk about in a moment. But really the reason to show this is what is this inner diameter thing. So that's the inner diameter, that's the diameter of the largest circle that fits completely inside the telescope primary aperture. And for LUVOIR B, we always talked about it as an 8-meter telescope, but its inscribed diameter was actually only 6.7 meters. And the reason the decadal focused on this inner diameter thing, that's sort of basically the usable, the part of the telescope primary that is usable by a chronograph. Okay, then we have HabEx. So HabEx was different in that it was, the primary mirror was smaller, but it had 2 different starlight suppression technologies. A chronograph, which is in here somewhere, and a starshade, an external free-flying starshade. The wavelength range was similar, just a little bit smaller, 4 instruments again, and there was a lot of commonality here. So there was a chronograph instrument that was similar to the chronograph instrument that was studied for LUVOIR, a camera, a high-resolution imaging camera, similar to the one we had on LUVOIR, and an ultraviolet multi-object spectrograph, which was also similar to the one that LUVOIR landed on. And then the one thing that was different was HabEx had an instrument specifically designed to work with its starshade, whereas we had an ultraviolet spectropolarimeter that was studied in France as a sort of internationally contributed instrument study. Okay, so that was the past. So now we move to the present and the future. Okay, so this was from just last month, a big team meeting in Baltimore. And okay, so here's our latest beauty pass. And I think you can see already, this is starting to actually look a little like HabEx and LUVOIR. It is sort of coming into sort of like, we're hopefully taking the best qualities from each of the 2 previous concepts and starting to combine them. So it's a little dark, I guess you can't see, but the primary is off axis, it's segmented, but there's a barrel on this time because for multiple reasons, stray light control, and maybe more importantly, micrometeoroids. So keep them off the primary. The LUVOIR's open architecture is a little too scary now. But I want to emphasize, this is not what Hab Worlds is going to look like. But, okay, here's some very preliminary specs, and I put twiddles everywhere. In every place I could, I put twiddles, because I want to emphasize nothing about this is set yet. We're at the very beginning. But it's 6-ish meters inner diameter. It's far UV to near infrared. Chronograph that has imaging and imaging spectroscopy is what this is sort of where we are right now, but certainly we want to think about taking a look at whether higher spectral resolution modes might be advantageous. Camera, high-resolution imager. One thing about this is that we want to try and do high-precision sub-microarcsecond astrometry on board Hab Worlds probably using this instrument for a couple of reasons. One, so that we can have the ability to measure the masses of the terrestrial, of the exo-Earths around sun-like stars that we may find, just in case EPRV can't get to the required precision on every single star that we need it to. We don't get to choose quiet stars. The stars will just be what they are. But also it has some very attractive applications for dark matter studies and for galactic center work like SAGE. and a ultraviolet multi-object spectrograph with multiple resolution modes. But the real key capability of this instrument is the fact that it would have a micro-shutter array or something like that, so it could get hundreds of spectra of different sources simultaneously. And so not only is it more sensitive, a big increase in sensitivity over Hubble, it's a big increase in multiplexing over Hubble because of that multi-object capability. And we have a fourth bay, which for the moment we are just leaving completely empty. So that's, feel free to speculate about what kind of instrument you would like to see in that bay. Okay, so I also want to talk a little bit about the principles that NASA has laid out for the development of Habitable Worlds Observatory. So first of all, we want to actually apply the lessons that we have learned from previous flagships. And this is a distillation of some of those lessons that we think will be very impactful. So first of all, and this is from the horse's mouth himself. This is directed from Mark Clampin at headquarters. So first of all, build a schedule. So this is something we've not done on NASA flagships before, but he said this time we want the mission schedule to be a level 1 requirement. So like we were a planetary mission that had a launch window dictated by orbital dynamics. Evolve the technology. So he said to build upon our current investments and our TRL-9 technologies. So for example, what we learned about segmented telescopes from JWST and from the Roman chronograph. Use next generation rockets. We didn't actually need to be told to do that by Mark Clampin, because why wouldn't you? But the nice thing about it, it enables larger telescope aperture sizes and potentially leverages, opens up a wider trade space in terms of mass and volume with those large fairings as well. Planned in-space servicing. So we are all in on not just making this observatory serviceable, but making sure one way or the other that it will be serviced. Now, with this will be probably robotic. We're at Sun Earth L2 with this observatory, so it's probably robotic. But we believe that we will be able to leverage commercial capabilities in in-space servicing by the time Habitable Worlds Observatory launches. Robust margins, more margin everywhere. So scientific, technical, and programmatic margins, they need to be bigger than they have been in the past, especially in the early stages of your mission development. And mature the technologies before you start your marching army. So in general, the NASA standard for how mature your technologies need to be at a particular stage is too lenient for flagships. We need to be more aggressive on our technology maturation than we have been in the past, is what that was saying. Okay, so those are the sort of the principles, the philosophy. Now we get to like what's actually happening. Okay, so Congress directed NASA in the FY24 appropriation, which is a law, directed NASA to start the Habitable Worlds Observatory Project Office at Goddard on this fiscal year, and we just found out, Mark Clampin announced a few days ago, August 1, that is the start date. So that's like really, really soon. This signals the beginning of pre-phase A, and I want to emphasize that despite the project office is at Goddard, this is 100% for sure going to be a multi-center effort. So what do we need to do in this pre-phase A? We need to explore the science, the engineering and technology trade space, develop our codes and models, and with the overarching goal, get everything ready to make good decisions rapidly once we're in phase A. Okay, so right now, to help us explore the science, technology, and engineering trade space, we've spun up a whole bunch of working groups. And here they are. This is sort of like a gradient. We've got ones that are science-y on the left, and ones that are engineering-y on the right, and then there are ones that are really kind of somewhere in between. I will emphasize that these are very likely to evolve in future with the start of the project office, but also most of these working groups do include international participants. So, oh, and I should say most of these working groups also have several sub-working groups as well. Okay, so what are they doing? So the science and joint working group activities, this is what they're sort of working on right now. And that is to start to flesh out and quantify our science goals and objectives. So it starts with a science goal. That's a high-level question. An example, just an example here, is like, for example, how did the seeds of solar system planets first come together? Then you have to go from goals to objectives, where you define the investigation, because there are different experiments you could use to tackle that science goal. For this one, here's an example. Discover trans-Neptunian objects down to sizes that distinguish between different planetesimal formation scenarios. Then you have to go from objectives to measurements. So this is what physical parameters you need to measure. This isn't, so for example, here it's 30 TNOs with diameters of 4 kilometers out to 40 AU. And it's important to also carry along with you why you're doing it. Constrain the small end of the size distribution at some sort of precision. I don't actually know what it is. So. And then finally, you get from measurements to observations, and this is where you really define it. So in order to achieve those measurements, you need to detect R of 31.5 magnitude objects at signal noise 5 in a certain region. So this is what the science working groups are doing right now. They're working on filling out multiple documents that are going through this flow. Okay, and that work will feed, for those who've seen it before know what it is, that this will feed the first 4 columns of a future science traceability matrix for the observatory. But in parallel to this, the joint working groups are trying to work on how we want to just not have point designs of science cases. We want to be able to understand the science returns from the observatory as functions of the observatory capabilities, and determine the slopes, the correlations, the derivatives. Where does our science return fall off a cliff? Where does it degrade smoothly? These sorts of things like this. So to do that, we're trying to start building an integrated science model that will connect to the integrated engineering model. And so our engineering colleagues took the leap towards integrated modeling like a long time ago. We haven't done that, actually, on the science side, and we need to do it too. And we've given it a name, Dynamic Integrated Science Return Analysis, DISRA. So it has a name, doesn't exist yet, but it does have a name. Okay, then on the technical side, we have the exploratory analytic cases. They are first round mission architectures that we are using to explore the trade space. So for example, we will use them to practice our end-to-end modeling, the integrated modeling, the stop modeling, and to sort of pipe clean the whole process, the whole design and analysis process. We will also use them to identify key technology gaps and guide maturation of potential technology solutions, and maybe rather importantly, and provide feedback to the rocket vendors as soon as possible to help influence their direction. Because, for example, the new generation of heavy lift launch vehicles doesn't quite actually exist yet. And there's still development work that is going on, and it is not too late to actually influence what those rockets actually end up looking like in 2040. Okay, so again, we don't expect that any of these cases that are being studied now will become a baseline design going forward. They are course models only. They're for exploration and practice. And this kind of shows you what we're talking about here. So that was JWST at the end of pre-phase A. Okay, that's the TRL-9 JWST. We're not even here. We're not even here yet. So you can fully expect that one of these, the pretty beauty paths I'm showing you, that's not what this is going to look like. Okay, everybody clear? Okay. All right, but these are the current 3 EAC 1, 2, and 3 that we're studying right now. We want to explore these 3 for about a year, and then we're going to stop, even if they don't close, even if we haven't solved every little detail about these things. But we're going to take what we learned and then fold them into a second round of EACs, where hopefully we take what we've learned and we'll have some new things that don't even look like this. So of EAC 1 that's the one I showed in the beauty pass. 6 meter inner diameter, 7.5 meter outer diameter, off axis. EAC 2, also off axis, but with a different telescope pupil. We're calling that a keystone. And then EAC 3 is, again, kind of, it's on axis, keystone, but larger, and it's larger to compensate for the, the detrimental effect of having the on axis obscured aperture for the coronagraphy. Okay. All right, so again, we're just getting started, and there's lots to do. So there are ways you can get involved with HabWorld. So first of all, we have a website, and you email list, HWO News email list that you can sign up for. We're going to start using it more than we have been. There's also the HWO Community Slack workspace. I think that link, that QR code will still work. And it isn't too late to volunteer for working groups and sub-working groups. If you want to do that, either email me for the contact info for the appropriate working group, or just put a message in the Slack. Okay, so again, briefly turning to the ELTs. So along with Habitable Worlds Observatory, the ASTRO 2020 Decadal Survey recommended significant investment in TMT and GMT as part of a US ELT program. And I'm just going to come back to just a little bit more about why ELTs for habitable planets around M-stars. So again, just to say what I said before, but a little more graphically, for the sun-like stars, we've got, okay. We have large habitable zones, but low planet-star flux ratios. So that means we need better contrast, but the telescope diameter can be more modest because the habitable zone is larger, and you can tolerate a larger inner working angle. So those are better suited for space. Then to the low mass stars, again, there's a higher planet-to-star flux ratio, but the habitable zone itself is smaller. So worse contrast, but huge telescope diameters, so you can have very small inner working angles. So these are kind of the sweet spots, in theory anyway, for ground versus space here. And between us, we would cover a wide range of different spectral types and try to really understand how habitability varies as a function of the stellar characteristics. Okay, I'm just going to end with this here, and it's just sort of a cartoony graphic of something of NASA's astrobiology fleet. And I like this because it reminds everyone that there's a mix. There's a mix of planetary missions here and a mix of astrophysics missions. And the search for life and the study of astrobiology really is a joint effort between astrophysics and solar system. And I'm not sure who's going to get there first. So I have a bet on, actually, with Thomas Zurbuchen. So that's it. So that was pretty quick, hopefully. And okay, that's it.
Super. Thank you for leaving so much time for questions, Aki.
That was my goal.
I'm sure it's very thought-provoking. So,
yeah,
I've got a, Catherine, could you get the question in the back?
Hi, my name is Natasha. I go to UCSD. My name is Natasha. I go to UCSD. How are the space-based and ground-based groups going to work in tandem to achieve the goals of HWO?
In tandem. That's a good question, and in the U.S., space-based astronomy is the purview of NASA, and ground-based astronomy is the purview of NSF or university consortia. And it is not easy passing funding between those two streams. That being said, for technology development and algorithm development and just experimentation, the ground-based high contrast community is sort of like, is forging the path So there is a lot of synergy and a great many things that the ground-based high contrast community can and are doing to help us. I'm not actually certain if we're paying that back, to be honest with you, space to ground. But maybe someone else, I don't know, maybe Dimitri would be better at answering that question than I.
Thank you.
Okay. Yes, certainly. On this, yep, that's a good point. Thank you, Vanessa. Also, there are precursor science observations that could help us with deciding how we design Habitable Worlds Observatory that can and should be done. There's some things that should be done now, and there's some things that can wait until much closer to launch. But I would say, full characterization, really good characterization of the potential target list would be excellent. I think right at this moment it's probably patchy, so that needs to happen because if you take targets away from your potential target list, that means you need to add worser targets to make up for them, and that the observatory must become more capable. So that's kind of important. Okay, thank you, Vanessa.
Cough, cough, reference stars. Roman folks know what I'm talking about. ENZ and then.
Who's going?
Hi, Yinzi at Caltech. I'm a grad student. This is probably an extremely biased question as a high contrast person, but I was wondering what the motivation for having a fourth empty instrument slot was, maybe the relative cost of having a fourth undefined instrument versus putting that money back into technology development for the other three. I wasn't sure if it was an architecture thing where there's reasons to have 4 instrument slots, or if it was I guess I wasn't sure.
Yeah. No, it's a fair question. I guess I will come back to re-emphasizing that Habitable Worlds Observatory is a NASA grade observatory, and a NASA grade observatory must serve a large swath of the whole of the astronomical community and planetary community for that matter too. It cannot be a unit tasker, and despite perhaps its key goal is to study habitable planets, that is not its only goal. So the more capable the mission is, the better. It needs to serve the whole community, not just a part of the community. Second of all, I actually think that having a powerful and capable and flexible observatory that it is good for all the science. And I think this because I look at, for example, Hubble Space Telescope, which had a similar, 4 or 5 instrument base, and people ended up using capabilities on Hubble that were designed for one thing, for something completely different, depending on what the universe actually showed them. I mean, when Hubble was designed, we didn't even know exoplanets existed, and the community used different instruments, some instruments which were intended for general astrophysics, to study exoplanets in really interesting ways. So I would say capability drives creativity, and just because that instrument isn't, quote, for you, doesn't mean you won't end up using it for your science someday, is what I would say about that.
Thanks, Aki, for a wonderful talk. I had a question about your twiddle. So the 30th magnitude, that's about 30 photons per square meter per hour in V band. Now, the HabX was a 4-meter off-axis with a star shade, so that's a very high throughput design. The minimum size of LUVAR was 8 meters off-axis, and then I think
6.7 for the inscribed, not so different, actually.
Okay,
Yeah.
and then 15 meters for the larger version. I wonder if it seems like the designs that are being considered are sort of on the lower end in terms of what previous groups had envisioned in terms of throughput. Maybe I'm wrong. Maybe you can disabuse me of this, but what's the sort of upper limit people would be considering for diameter?
Well, like all space telescopes, the ultimate limit is your launch vehicle. You know, it's like the dome for a ground-based telescope. I would say that we are still exploring what sizes of telescope architectures can fit into different variants of the future launch vehicles. So I don't think I can answer your question right now about upper limits. So.
Hi, this is Brent from UC San Diego. I'm interested in asking why, for Habitable Worlds Observatory, an off-axis design has been selected, at least for the near future. What would you consider to be the greatest advantages of the off-axis design as opposed to an on-axis one for a space telescope?
So I want to come back and repeat something I said earlier. Nothing about this observatory is decided. Okay, nothing is selected. And come back here. So of these, we could take a closer look, for example, at these EACs. This one's off-axis, off-axis. That one's on-axis, because we want to actually understand the trade between how much bigger would you need to make the telescope to compensate for the degraded coronagraph performance of an on-axis telescope. Because this one, I think if you can see, this is really long. To make it off-axis, the secondary mirror has to be quite a bit further out. That's easier to pack into a launch. The on-axis is easier to package into a rocket fairing in general. So there's a trade space here, which we are actively exploring. So I don't know yet. We don't know yet where the optimal solution is going to be. Be bigger and on-axis, smaller and off-axis? We don't know yet. So.
Hi, I'm Michael from UC Santa Barbara. You mentioned that NASA wants to use more mature technologies than previous great observatories. I was wondering what TRL that translates to today and what the technology development timeline looks like.
Gosh, I don't know. There's a lot of technologies involved in this. They're at a mix of TRL levels. I would say they're sort of in the mid TRLs right now, 3 to TRL 3 for some things, TRL 4 or 5 for others. The NASA's requirement officially is that you must be TRL 6 by Principal Design Review, PDR. That's the end of Phase B. That's too late. We should pull that forward. All I can say right now is that the technology development roadmap, that's our key deliverable for the next 6-9 months, I would say, right, Bertrand? Yes? Yeah. So come back in 6 months, maybe I can tell you what our technology roadmap is, but we're going to have one very soon. So.
Thanks so much.
Okay.
All right, and I think that brings us to break. And we will be, so let's thank Aki again for an excellent talk.